Albert Einstein's theories rank among humanity's greatest achievements. They sparked the scientific revolution of the 20th century. Einstein and his successors made 3 predictions in their attempts to understand how space, time, and matter are connected. First, that space is expanding from a Big Bang. Second, that black holes exist, these extremely dense places in the universe where space and time are tied into contorted knots and where time itself stops. And third, that there is some kind of energy pulling the universe apart. These 3 predictions seem so far-fetched that everyone, including Einstein himself, thought they were unlikely. Incredibly, all 3 have turned out to be true.
Now, we've made recent observations that tell us that we have to go beyond Einstein's theory of space and time to understand the nature of the universe.
This is where NASA's Beyond Einstein program begins.
Beyond Einstein attempts to answer 3 fundamental questions. What powered the Big Bang? What happens at the horizon of a black hole? And what is the nature of dark energy that permeates the universe and drives its expansion today?
Using advanced space-based technology to explore these 3 questions, NASA and its partners begin the next revolution in our understanding of the universe. The Beyond Einstein program stands on the shoulders of other missions within NASA's Structure and Evolution of the Universe program. Missions like WMAP, with its detailed all-sky picture of the remnants of the Big Bang.
WMAP has determined the content of the universe, how much atoms, how much cold dark matter, how much dark energy. It's determined the age of the universe quite precisely. It's determined the shape of the universe, and is even determining some of the properties of the very earliest moments of the universe.
Beyond Einstein also builds on the discoveries of the Chandra X-ray telescope, which found that black holes are everywhere. The program is a well-coordinated mix of facility-class spacecraft, probes, and Pathfinder missions, each employing powerful new technology. In the facility-class range, Beyond Einstein supports 2 large spacecraft called the Einstein Observatories, LISA and Constellation X.
Constellation X is an armada of 4 X-ray telescopes that will work together in unison to simultaneously observe very distant objects. With their data combined, these 4 telescopes will be 100 times more powerful than any current X-ray telescope.
This power enables ConX to probe the secrets of matter and energy at the very precipice of space and time, a point where matter crosses a black hole's event horizon, never to escape again.
One of the science goals of Constellation X is to search in the darkest regions of space for the mysterious dark matter, and that's the 90% of matter that we can't actually see, but cosmologists know must exist. There's material out there holding together clusters of galaxies gravitationally. These galaxies otherwise would fly apart by virtue of their own motion, but there's something there holding them together gravitationally, and that's what we believe the dark matter is.
The other Einstein observatory is LISA, the Laser Interferometer Space Antenna. With LISA, NASA and the European Space Agency teamed together to search for another of Einstein's predictions: gravitational waves. These are the barely perceptible ripples in the fabric of space-time that distort matter and cause it to bob like buoys on the ocean.
LISA should be able to see supermassive black holes merging. We expect to see the small black holes getting eaten by the big black holes, and we would expect to see thousands of compact stars closely orbiting each other in the galaxy, and we might see some of the echoes from the Big Bang. If we could detect the gravitational waves that were made in the Big Bang, we could actually see back to the earliest possible moments of the Big Bang.
To achieve the extreme sensitivity needed to detect gravitational waves, the LISA mission uses a triangular formation of 3 spacecraft, flying approximately 3.25 million miles apart and connected only by a laser beam.
We measure the separations to a very tiny fraction of the nucleus of an atom. So we're watching for very small motions, relative motions, between those masses.
Very recently, cosmologists were awestruck to discover that the universe is not only expanding, but that the expansion is accelerating. This unknown force, dubbed dark energy, has become one of the most important questions facing cosmology today.
Dark energy has an effect on the expansion of the universe, but we also believe it arises from microphysical processes at the quantum level. And particle physicists and cosmologists are getting together to try to answer the riddle of dark energy. And we're doing it together in a joint dark energy mission.
The U.S. Department of Energy and NASA have partnered for that mission. It's just one of 3 probes planned in the Beyond Einstein program.
It will probably determine the ultimate future of the universe.
The technological advances, the science advances from LISA, Constellation X, and the Einstein probe missions all pave the way for the ultimate vision for the Beyond Einstein program, the ability to look back to the very beginning of time and space, and the means to directly observe matter as it falls into a black hole. NASA's Beyond Einstein program is poised to complete Einstein's legacy and ultimately unravel the mysteries of the universe. The adventure awaits.